a couple of minutes more, but please, we would like to tell you that it will be a recording session, and it will also be uploaded on the social media of the DRIVE project afterwards.
Okay, thanks, Georgia. I think we can start. So hello everyone, and welcome to the first webinar of the DRIVE project. Before we get started, we would like to go over a few items, so you know how this event will go today. As Georgia mentioned, you will have the opportunity to submit text questions to our presenters of today. So please type your questions into the Teams chat, then we can collect them. Your microphone and video will be off during the webinar. And you can send questions, of course, at any time during the presentations. And we will collect the questions and address those in the Q&A session at the end of the presentations. And any questions that cannot be handled today in the session, we will, of course, respond to offline to you directly. This webinar will be recorded, and you can watch it back on our website and YouTube channel. Also, a lot of information about the project can be found there. And you can also subscribe to the DRIVE newsletters that will be sent out every 3 months, addressing all kinds of interesting topics of the project. In this first webinar, we will focus on the objectives for the projects and share information and some first results about the technologies we're working on. And today we have the following agenda. First, I will give a short introduction of the project and its objectives. After that, our presenters of today, Peter Moser from NWE, Katrina Simwes from TNO, and Diego Pinto from HOVYU, will share technical information of the DRIVE project. I will close with some insights on our next steps, and then we will try to answer your questions. So enjoy the webinar, and I will first start with the project introduction. So I'll start with the project introduction. First, some words about the consortium. The consortium is constellated from partners from research and universities, industry and an NGO. TNO, ITMEC, Harriet Watt, and TU Eindhoven are the research institutes active in the project. RWE, SSE, HOVYU, CEMEX, and TotalEnergies are the industry partners, and IED's NGO and dissemination partner. We have a very international consortium. We have 8 countries in the project, so that's quite, we spread over the whole of Europe. And we have a total budget of a bit more than 4 million euros in the project. And we receive funding from the national funding organizations of 2.7 million. And the total person months in the project is more than 350. So we have a lot of work to do in this project, and we now a bit more than a year on the way. These are the work packages in the project. So work package 1 and work package 0 and work package 1 are more about the management and the communication with our funders, the CTP organization. And work package 2, 3, and 4 are really the technical work packages. So in work package 2, we look at deep removal via thermal regeneration processes. In work package 3, we look at deep removal via electrochemical regeneration processes. And work package 4 concentrate on the techno-economic and life cycle assessments. This is a graph that we made in the project proposal about the work that we do in DRIVE. So the thermal regeneration technology is based on amine CO₂ capture, and where we go to very deep removal rates. in the electrochemical regeneration, we look at 2 technologies for electrochemical regeneration that are being also further developed into the project. And we have a technical economical work package that looks to a lot of cases, different cases: cement, waste to energy, coal-fired power, and combined cycle power, and also for a lot of different cases considering capture rates. And we also want to, of course, to compare the thermal and electrochemical regeneration processes. This is an overview of the TRL levels that we have in Drive. So CODEC and ZEUS are being further developed into the project, I would say. There was already a basis, but we'll try to optimize both processes and demonstrate it in the lab, and also increase the performance of both processes. In the lab, we will also test it with a CO2 capture plant. We have a small complete CO2 capture plant, which is called the mini plant, and both technologies will be operated in the lab. And then one of the technologies will be selected for an on-site operation at a plant of Cemex in Czech Republic. And then we will transport our mini plant and one of the 2 electrochemical setups there, and also operate there with the flue gas of the Cemex plant. Of course, the CO2 capture with amines has already a much higher TRL level, and we are using the CO2 capture plant of RWE in Niederaußen to really look into the deep removal of CO2 using this plant. The project objectives, we really want to demonstrate deep removal at TRL 7 at the RWE plant with CODEC solvent. Quite some campaigns have already been done, and we are still further testing the solvent. And we concentrate on the energy demand, of course, emission degradation, and how it will operate. And Peter Moser will tell more about this in his presentation. Katarina and Diego will present the electrochemical regeneration technologies that we want to further develop in the project. And in the end of the let's say in the last year of the project, we will operate one of the electrochemical setups in the Czech Republic, and also have a clear target also for the energy target that we want to reach. And of course, at the end of the project, all the results about the technical, economical, and LCA will be presented and published. What we really want to do is develop this electrical regeneration method much further, try to make steps in TRL level, and also see what it can mean for us and what it can mean for the CO2 capture community in terms of performance and emissions and things like that. We really want to see if for the amine technologies, if very deep removal technologies work, and what will be the cost of it in terms of extra costs for energy, degradation, and things like that. So we really want to look into that. So we have a very big demonstration activity in Drive. And we want to look for these multiple cases, what the benefits will be in different scenarios. We tend to do a lot of dissemination in the project. So we already have a website which is already active for since the beginning of the project, where we will present our newsletters, results, and also the recording of this webinar will be uploaded into the website. We have a LinkedIn page where we can regularly post news about the project. And we have a YouTube channel where we also post video material about the projects. We're also preparing some video material about the working of the technologies that we develop. And of course, we also try to be present at the major conferences to disseminate our results. So this is still an overview of our partners. I think we have a very nice consortium with a very technical, very specific targets. So that gives also a good direction to the project. And of course, we want to thank our funders to make also this project possible. So this is a very short introduction. I think we should now switch to the technical work packages, and I would like to hand over to Peter Moser from RWE to present on the thermal regeneration results.
Okay, thank you, Peter. I will share my slides. And yeah, I want to start my presentation about this work package 2 on thermal regeneration processes for deep removal with an introduction of the objectives of the work package. So our main goal is to confirm technical feasibility, and we are not talking about deep removal, so to achieving highest capture rate for just some hours. No, we are talking about 24/7 operation in long duration tests. And yeah, we want to understand and assess the impact of deep removal on the key performance indicators, energy demand, emissions, solvent degradation, but also operability. Do we see effects you normally don't see at normal capture rates achieved at amine-based capture plants? And we hand over then this data to our colleagues in the other work packages for life cycle analysis, but also for sure for techno-economic analysis. So that means that we can validate the modeling tools and understand what's going on in a process with deep removal, so that it can be then also scaled up for different use cases. So we have a quite holistic approach. Our setup is that we use for the testing at Niederaußen the flue gas of a 1000 megawatt lignite-fired power plant. Our solvent is this aqueous blend of AMP and piperazine, so the so-called CESA-1 solvent, which is, well, you can say now the working horse of the scientific community in Europe, especially. But there are also, I think, more and more commercial interest in the solvent. Our flue gas composition is around 14 to 15% by volume of CO2 and around 5% of oxygen. Important is when we talk about this highest capture rate that we use also frequently calibrate our infrared analyzer for the depleted flue gas. If we have just then the very low traces of CO2 in the flue gas, and we use a calibration gas with 200 ppm of CO2. We tested different emission mitigation technologies. Benchmark is always a water wash. This is important because we use this also. This is the most easiest configuration in the end, and this helps you to understand the process. But we control the emissions then with a dry bed, or name OA0 zone, but also with the acid wash. And when we use the acid wash, we usually also vary the pH value. And what I want to point out, we achieve this highest capture rates without any additional equipment in the plant, so no increase of heat exchangers or more reboilers or a mechanical vapor recompression or things like this. No, we use it as it is, and we will write then for the parameter testing the flue gas flow just one time. Normally we operated under full load conditions regarding the flue gas flow, but then we vary the solvent flow, the desorber pressure, and we have then also variation between using the full length of the absorber with 4 beds with structured packing or just with 3, the so-called then also dry bed configuration, which at the same time reduces emissions. And we have also varied the position of interstage cooling in the absorber, or also tried to operate it without an intercooler. Coming to the testings, we realized until now we have in total 5 testing campaigns, and 4 have been already realized. So we had, in the first, we operated the plant, really tested whatever is possible to receive some hands-on experience on this highest capture rates, and have also a nice set of data for the modeling tools. And then in the second campaign, we operated with 3 active beds. In the third campaign, we had 4 active beds. And I also have to explain that we have no permanently installed reclaiming system in the capture plant, so all trace components or degradation products will accumulate. After in total around 15,700 operating hours, we exchanged the solvent, and this was a request from another ongoing project at Niederhausen, and this was nice because then we had also fresh Caesar-1 solvent in the plant, and this is interesting to compare the performance. And you can see here, this is a power plant output. So when we have no flue gas, the power plant has a stint cell, we cannot operate. But then here during this test, we write significantly the solvent flow, so doubled it or more than doubled it. And that's just to explain a little bit how we tested it. Coming now to the results regarding the key performance indicators. So this is not astonishing. When we go to highest capture rate, we see quite a steep increase of the boiler duty. So for Caesar-1, we see that it's not so dramatic, perhaps until 99% capture rate. But if we go to highest capture rates, it significantly increases. Nevertheless, you can say perhaps so until this range of 98–99%, it's a moderate increase of the specific reboiler duty. It's around 30%. Regarding the aging of the solvent, the effect on the reboiler duty, this is more or less linked with the amine concentration in the solvent, and by degradation, depending on your solvent management, you are replacing in the end active amine by degradation products, which sometimes have also still an amine group in and are active or provide alkalinity. Nevertheless, you have more and more inactive stuff in your solvent, and that reduces the efficiency in the end of the process. And that's also what we see. So when we here as an example 4-bed operation and 1.7 bar in the absolute in the desorber as operation parameters, we see then that we need for the H solvent perhaps around 10% more energy, and this is mainly linked to the lower amine concentration. Also important is the topic emissions, and we could confirm also that at highest capture rates, this is here, I think it's in the range between 98 and higher than 99%, but we see that the effect we have seen already in this accelerating CCS technologies project scope, which ended last year. We can confirm this also for highest capture rates that we see in an increase of the emissions for a fresh solvent. So, and nevertheless, we have also to say the emissions are quite too high for operating a plant with these emissions here, especially for AMP. But these data are important to understand the mechanisms of the emission formation. Coming to the next slide, this is then to show that we have quite effective emission mitigation technologies available. So emission control for deep removal that works. Here you see also that we have also tested it under full load conditions of the power plant, but also part load conditions. So typically the emissions are a little bit lower at part load because we have less CO₂ in the flue gas coming from the power plant, and this means less heat of reaction the carbamate formation is released in the absorber, and then the volatile emissions go down. You see also here the increase of the ammonia emissions. This is linked because we had also here variation of the pH value, and here we came a little bit more than less acidic. So higher pH value. Nevertheless, we have quite nice low emissions. Important is to use the parameters data from the parameter test for the evaluation of the modeling tools, because in the end they will be also needed for the techno-economic analysis. And these are two diagrams we published already at the GHT 17 conference. This was a result from 25 parameter tests. And yeah, what we can say is that really it is quite good prediction of the behavior of the capture plant. So we can say that for example, this key performance indicator capture rate is within 2% deviation from between experiment and what the model predicts. So this is nice. And what's also really promising is the prediction of the emissions. So this is also quite nice working. For sure, you always have some scattering, and we see some underestimation of emissions, which we are further investigating. So there might be two reasons. One is that the equilibrium data might be still not, they have become much more better also as a result of the scope project. Nevertheless, there might be still some deviations. And the other is that we might have to explain it by aerosol-based emissions, which cannot predict it by the modeling tool. So we use here this ProTreat model, which seems to work quite well. And yeah, we demonstrated deepest removal. So we have reduced the CO2 concentration in the depleted flue gas down to 91 ppm. So this is really, really low. If we compare it with the concentration in the ambient atmosphere, we have, we have to say 50% more specific energy demand that we need for it. So, and you can say that we capture in the end CO2 from the combustion air of the power plant. And this brings me to the conclusions. So we have finalized 4 of the in total 5 testing campaigns, and yeah, we have shown it that it, in principle it works, and we have more than 3,800 operating hours now with capture rates of higher than 98%, and yeah, also CO2 concentrations below 100 ppm are possible, and this was also one target really of the DRIVE project. But we also have to point out that deep removal means a trade-off between highest achievable CO2 capture rates, climate protection, but on the other hand, it means also higher energy consumption. So, and what is now the conclusion from it? This will be the result of the techno-economic analysis and the life cycle analysis, which will investigate this for different use cases. We know that emissions can be controlled, and it seems that we have quite nice simulation tool available also to describe the behavior of the plant for this deep removal conditions. And from October this year, it is planned to realize the last testing campaign. This will be a continuous 6 months operation at deep removal conditions, and we will there learn then more about solvent degradation under these conditions, and this will be then also finalize the handover of data for the techno-economic analysis and the life cycle analysis. And also I want to thank our funding agencies, and now I will hand over to Katharina.
Thank you, Peter. Okay. So Hello, everybody. My name is Catarina Simões. I will be presenting work package 3 on the introduction to CODEC and ZEUS technologies, also with Diego from HOVYU. So the work package 3 is about the deep removal via electrochemical regeneration processes. And the objectives for this work package consist in optimization of the electrochemical regeneration for a minimal energy requirement of TRL4. And this is the goal we are busy at the moment with. Afterwards, we'll go for the validation of the integrated absorption regeneration combination at TRL5. And afterwards, one of the technologies will be brought to demonstration for the electrified CO2 capture at TRL6 at the industrial location. Why do we want to electrify the regeneration of the CO2-rich capture solvents? There are several reasons. Here you can see a few. So we can regenerate inorganic capture solvents in reducing the need for using amines. So in this case, we can use the inorganic salts like potassium hydroxide, which also means we have no issues on degradation. And also we can operate at a room temperature, which also influences the reduction on thermal costs. We can couple this electrification with the renewable energies, so delivering an electrified solution. And it can be integrated in existing industrial processes. There's also the easiness on the scalability, because the electrochemicals reactor are based in a modular design, and we can avoid the harmful byproducts since the regeneration of the KOH is constant. And how do we do this? So we do the regeneration via electrochemical pH swing. Here you can see on the plot the speciation of carbon through the different pHs. So when the CO2 is absorbed in the absorption column, it is around pH 12, so in the carbonate phase. And the idea is to shift towards the lower pH side, where we go from carbonate to bicarbonate and finally to carbonic acid. Once we are in the carbonic acid region, as you can also see here on the equations, we reach the equilibrium that carbonic acid dissociates into water and CO2, and this way we have the gas being separated from the liquid. So that's where we want to achieve the separation of the CO2, and the pH swing is based on. I will now talk more directly about the introduction to CODEC, which we call as the direct electrochemical regeneration. And how do we do this? So it is a direct regeneration because we do a single-step regeneration. This means it's all within this electrochemical reactor. And in one side, we'll have the CO2 release at the anolyte by acidification, as I showed in the previous slides. And at the same time, in the catholyte, we are regenerating the KOH, which can be directly used in the absorption step. And the goal of this process is to get an optimization towards 3 gigajoules per ton of CO2. Here is the schematic how it is working now in the lab in the first tests. So the solution, now it's synthetic, would come from the absorber with the rich in carbonates and some bicarbonates. This is fed to the anolyte. The ions dissociate. And at this point, the potassium will go towards the anolyte, the catholyte, since it's attracted to the negative charge. We also have water present in the system, and this will oxidate at the anode, producing oxygen and protons. The protons will react with the carbonate, and we then release as CO2 from the carbonic acid and also with oxygen. The water can then be fed to the cathode, where it is reduced, and here we produce hydroxyls and hydrogen. The hydrogen will simply leave the system, while the potassium and the hydroxyls will react together, giving us the potassium hydroxide And we have our regenerated solvent that can be again used for the absorption step. This is how the setup looks in the lab these days. So we have here in this compartment our electrochemical reactor. Here on this side is all the coordination of the sensors. Then we have also here the pumps, the gas management, and behind are also the tanks, which can go to up 60 liters capacity. This is a simple schematic how it is looking in operation. We are now doing batch situation, so the anolyte is recirculating in this side. We measure in line the pH, conductivity, temperature, and pressure, and we also are making liquid samples. And the catholyte is a mirror of the anolyte, but in the anolyte we still have a CO₂ analyzer, so we can quantify how much CO₂ is released from the system. So we are doing optimization of CODEC. The parameters we are looking into are conductivity promoters, also into the compartment geometry in the reactor, solution composition, the applied current, which will also change the CO₂ release rates. And finally, we want to implement gas diffusion electrodes to improve the system. And this we do because it will reduce potential losses, and also it will avoid the mixture of CO₂ and oxygen, which was something still to close on the last configuration. We want to have a pure CO₂ outlet and not a mixture. So in this case, you can see the setup becomes a bit more complex, and we have now two gas compartments from the extra through the anolyte and catholyte. And we basically have a loop of hydrogen where we feed hydrogen to the anolyte, and this reacts instead of water. So now we don't have oxygen evolution. And the rest of the system is rather similar. So for upcoming activities, today was just about showing how the technology works. We are now finalizing the CODEC optimization with the application of the gas diffusion electrodes testing. Afterwards, the plan is to integrate with the absorption step, so the mini plant. You can also see here pictures how the mini plant looks like, and both setups will be integrated together. And with this, we'll have a 2-month campaign with synthetic flue gas. So we'll make an automated continuous system at this point to test it. And depending on the performance, there might be a 2-month campaign on site with flue gas from the cement factory. With this, I would also like to acknowledge the funding agencies and thank you for the attention. And I'll now pass the word to Diego to continue on work package 3 with ZEUS.
Yes. Okay. It seems that my camera is not willing to switch on. So let's see if I manage now.
No, we will try to solve this. Oh, now it's
Yeah.
okay.
Okay,
Great.
I'm here. Yes. Okay, so continue on work package 3. I'm going to present now the second electrified technology, which is called ZEUS, and that stands for Zero Emission Ultra Stripping. For that, I just want to give a small overview on a traditional amine-based process, which is the state of the art nowadays for capturing CO₂. So the traditional process, as you may be aware of, we have the absorber that removes the CO₂ from the gas, and then the solvent is sent to a stripper, which works with the regeneration, a thermal regeneration, as we see Peter Moser presenting the RWE plant. Then CO₂ leaves at the top of the stripper, and the regenerated solvent goes back to the top of the absorber. In our case, and that's more or less the same of CODEC, we want to exchange the regeneration part to a electrochemistry-based regeneration step instead of using thermal energy. And the ZEUS concept will look like this. So the absorption part will stay more or less the same. Instead, the regeneration part will be exchanged to the process that is respective to what we want to achieve with electrifying it. So basically what we can achieve with ZEUS is that we have a two-step regeneration system that's a little bit different from what Katarina presented now. So we have a first step where CO₂ is released, and this CO₂ can later be released under pressure. And then there's a second step where you use electrochemistry to regenerate the agent X, what I call now, and the solution that goes back to the absorber. So a little bit on an overview on ZEUS. As I mentioned, the name stands for Zero Emission-Ultra Stripping process. We can strip CO₂ at ambient temperature, as you can see here in the picture. So the small bubbles here, those are the CO₂ actually being stripped from the solvent. This process was filed a patent for that. So and now we are planning to optimize it and implement in large scale. There is a potential to produce CO₂ up to 10 bar. So we did some tests, desorption up to 9 bar, and we managed to achieve desorption under those pressures. And the chemicals we use, they are easy to handle and easy to find. Just a comparison, we did a theoretical comparison with MEA. MEA targeting 95% removal for if I'm not mistaken here, this is a waste to energy case, and also using two types of solvent under the ZEUS technology. And we managed to achieve below 100 ppm with ZEUS, and that will be confirmed now in the next steps for the experimental plan. Just the status where we are now. So we have a partner, the Eindhoven University, which is working on the development of new materials for this process, and they are now characterizing and optimizing a new membrane to be used in the bipolar membrane part. Those are now on lab scales test, and it will be used for the scale up test that we plan to do. We also built a skid for demonstrating this. The capacity of this skid is about 3 kilos of CO₂ per hour. The skid is finalized, so we are now integrating the electromembrane part, so we can optimize, and then we will bring to TNO for integration with the absorber, and then we can simulate, or not simulate, but validate the whole process, absorption, desorption. And TNO mini plant has a capacity about 1 kilo per hour, so our speed is well fitted for that side of. Yes, for that, I'd like to acknowledge also the funding agencies, in special in our case for HOVYU. And yeah, I'll conclude my presentation.
Yeah, thanks a lot, Diego. So I hope we were able to give you a taste of what we are doing in Drive, and also on the current status. I have a very few slides on the work that is coming, so I will also put them up. So what's next? Yeah, as Peter already mentioned, we're going to do some further testing at the RWE pilot in Niederhausen. In much longer campaigns, we've had a few shorter campaigns. Now we're also doing longer campaigns to address the degradation and emission behavior in deep removal. Yeah, we think as a consortium, it's really key to have this longer-term campaigns to really see if there are any disadvantages that pop up when you test a lot longer. So it's really nice that we can do this in the project. And of course, the RWE CO₂ capture plant is already existing for a very long time, has many operation hours. So we could also immediately start testing this kind of technologies in this plant. So that was really nice. Also, we're going to do further testing of the CODEC and ZEUS in the lab to optimize the configuration and to determine the performance. A task also in the first year of the project was to define the KPIs to really also see how we're going to compare both technologies and how we're going to say, okay, this technology is more suited to go on site than another technologies. So we really have done a lot of work to define this KPIs as a consortium, and the KPIs will also be published in a later stage, so they can also we learn from the world to see how we do this kind of comparison. And then next year we are going to transport the equipment that's going to be tested on site to Czech Republic. We already have done a kind of exploratory campaign where we also measured the flue gas of the plant of Cemex, that we know a bit what is lying ahead of us when we go testing there on site. And of course also to see the plant where we can build up the equipment, what is needed on utilities to run the equipment on site. So that's already ongoing actually from the first half year on, that we really working very closely with the plant to make this demonstration possible. And of course we have the technical economical evaluation and the LCA. So what you can see in this picture are all the use cases that we're going to evaluate for the different sectors, for the different technologies, for the different deep removal rates. Yeah, if you count them all, you can see that there are 48 scenarios that we're going to evaluate, so quite a lot. And from the scenarios, we will select 8 for an LCA. So also from this work package, there will be a lot of results becoming available towards the end of the project to see how these technologies work in the different use cases, how they perform, how they compare, and also maybe see if for one use case, maybe one technology might be preferred over another technologies. But that is more for the last 1.5 years of the project. And of course, we will keep disseminating our results. So please have a look at the website, register yourself for newsletters. Then we'll keep you updated. There will also be more of this webinars because we like to inform everybody about the work we are doing and the results we are achieving. So that's it for the presentations. So now we can, I think, begin to answer any questions that have been submitted in the chat. Of course, you're most welcome also to now type your questions in the chat. And I see already a first question in the chat from John Gibbons. Peter, I don't know. I mean, you can also read the question, right? So maybe you can answer the question of John Gibbons. And maybe all the presenters should switch their cameras on at the moment, yeah. Including me.
Okay, yeah, hello, John. So the question also for the others, really, do you have any estimate for heat losses from the thermal solvent regeneration stages? And if so, have you included a correction for heat losses in the SRD value reported? Best wishes, John Gibbons. So heat losses in the end are taken into consideration, but to be honest, this is more a question for this very small testing facilities. It depends if you have trace heating, if you have insulation in your plant, and also this topic is the diameter and the end of the absorber. So what's the ratio of let's say, surface of your plant compared with the volume of solvent that you're using? So, and we know it from the beginning of the testing in 2009 from our pilot plant, where we carefully analyzed, where we used monoethanolamine as a solvent, that these heat losses are negligible for us. And therefore, it's also applicable for CESA-1 solvent. It's not just for monoethanolamine, it's a general answer. We know it, and we have also seen it from this very, very good fit of the results when we compare the modeling results with the ProTreat software with the real data. So heat losses is not the topic.
Okay, I think we have another question about the ZEUS process. So maybe Jaco, you can address that one.
Yes, I'm still struggling to switch on the camera. So apparently I have, oh no, yes, I managed. It's a hardware problem, apparently. Yes, do we generate 1 mole of oxygen for 1 mole of CO2? No, in this case, there is no exchange of oxygen for CO2 in the ZEUS process. So there is no degradation.
Okay, thanks. Just Rafus just mentioned that everybody is now able to unmute themselves. So if you want to speak, then please go ahead. Maybe Katarina, you can take the question of Christoph.
If you have other strong acid components, SOx, NO2, chloride, in your real flue gas, will they be co-absorbed and will be released during electrochemical regeneration as opposed to HSS with the CO2? So most of the compounds, we did a pre-test at the CEMEX campaign to see which of the components in the flue gas would influence the flue gas on the absorption step that will be then feeds to the electrochemical regeneration, and we didn't see that we would have a lot of impurities. We don't expect any reaction in terms of the SOx. We did not see any chloride and fluor that would influence, so we haven't tested it. So it should be in concentrations very small that will not react. The nitrates might be the one that we need to keep an eye on it if it arises the concentrations. But if the levels will be ppm, we should be on the safe side and not have any release during the regeneration part.
Yeah. Okay. Thanks. Maybe I can ask a question to Peter. How do you see the very deep removal rate compared to the extra energy that we need? I mean, and how are you really gonna assess that in your plant?
Yeah, and this is not so easy to answer, and this is exactly, I think, why we need also this project, because it's not so simple said. We hear more and more in this time, yeah, you have to achieve highest capture rates, but this is a trade-off. We have capture, this highest capture rates are not achieved with nothing. We have to spend energy for it. So we have to answer where comes this energy from. We have to answer what costs are related to this. So, and in the end, there's this overall picture of techno-economic analysis and then the life cycle analysis, putting this together for different use cases will answer what makes sense. To say it more clearer, if you have a chemical waste incineration, and you don't use the waste heat from this plant, and it has the right temperature level, okay, then perhaps energy efficiency doesn't matter, because anyhow you have to cool it away. Then let's go to higher capture rates. And if you would have higher degradation rates of your solvents, because you would really boil it and cook it and would increase further and further the steam generator temperature or let's say the reboiler temperature, then you can perhaps burn it in your facility by your own. So then it's cheap and simple. But for other applications, they even have not enough heat available to achieve perhaps a 90% capture rate. We have to also think about that we see more and more this development in the direction of heat pumps or of e-boilers. As an example, our pilot plant at Niederaußen is not using steam from the power plant. It is an electric-driven steam generator. If it's renewable power in the future, which is very cheap, this would be then also different from a situation as it might be today. So this is very complex, but just I want to highlight, we show that things are technically feasible, but if it makes sense for the society, it's not so easy to answer. And the facts should come from projects like DRIVE.
Yeah. Okay, thank you very much. There's also a question about how the electrochemical regeneration compares to the thermal regeneration with heat pumps. And yeah, Diego, working at HOVYU, being active in both technologies, so maybe you can shine your light on this, Diego.
Diego, you're muted.
Sorry. Yeah, thanks, Catherine. Yeah, that's a very good question. How to answer this? There are two different principles, and because electrochemistry is working on the molecule side and the reaction side, and the heat pumps is a device to use to generate heat, basically, electricity to heat. What I can answer is that the heat pumps also now there is quite a lot of developments because the temperature levels that we need to regenerate the solvent, the heat pumps may at the moment for large scale, as far as I'm concerned, the efficiency is not very good to achieve this 120 degrees, for instance. And one difference in electrochemistry regeneration is that we can do this in a more lower temperature side. There are it's two different ways, but yeah, it's two different ways to electrify the process.
Yeah. Okay, thanks. Katrina, there's also a question for you, right, in the chat.
Yes, so what is operational stability and lifespan of the electrolyzer in terms of the membrane and electrodes used in the CO₂ regeneration processes? So at this stage where we are now, it's not, we don't have an exact value to say, but in general, life of electrolyzers and membranes, membranes are usually in a lifespan of around 4 years, if I'm not mistaken, depending also on the process conditions. So in this case, since we are using a acidic side and a very alkaline side, I would say that should be where we land. And the electrodes, this should last a bit longer, but we also don't have an exact number at this point. So now we are more in the optimization and making it work towards the 2 months. And then the full time scale needs to be seen further on. But a reference case would be then the chloralkali electrolyzers, for example.
Yeah. Okay, thanks. Diego, can you say something about the KPIs that we are using in the project? Because, I mean, you were very involved in setting those up.
Yes. So, I mean, for this project, we want to measure the energy consumption. That's one of the main KPIs that I think Peter, you presented also the target costs there that we in the beginning of the project we estimated that we can achieve. There are a few other KPIs, and that goes for amine-based and also for electrolytes, for instance, is the loadings, the amount of solvent that is required for makeup. I think, if I'm not mistaken, Peter, this is going to be a public report, the list of KPIs,
Yes.
right? Yeah.
Yes.
And that we can, we're going to disclose all the numbers, but mainly is energy and costs. It boils down to energy and costs in the end. And
yeah, that's the main KPI indeed.
Yeah.
Thanks.
There are also, Peter, sorry, there are also two people, John and Christoph, that raised their hands if they want to jump in.
I just noticed indeed. Yeah. So, John.
Yeah.
Go ahead.
Yeah. Can you hear me okay?
Yes, we can hear you.
Yeah. So just very quickly, please. It's to do with another project actually. When you said negligible, did you mean less than 1% heat losses?
He's just muted.
You're muted, Peter.
Yeah. Yes, but please be careful, John. You must calculate it for your plant. So, and typically the small scale absorbers, especially, where you have then heat release. This is a little bit tricky, and often, there you see then losses. But it's also perhaps makes a difference if it's inside a building or if it's let's say more real world outside. So this might be also have an influence, or if it's in Greece or in the northern part of Norway. But as I've mentioned, I'm pretty sure you know all our publications also about monoethanolamine and CESAR and the thermodynamics, and we don't have an issue with heat losses.
But just to be clear, for your plant, negligible means less than 1%.
Yes.
Thanks. It's to do with TCM actually, which is a different place, but it's a big one. I mean, our small heat losses are much higher, right? Anyway, thanks very much.
Yeah, thanks, John. Christoph, you also had your hand raised.
Yes, thank you. I have a question probably to Peter. When we do deep CO2 removal, I would expect that your lean solvent needs to get leaner. That means you need to strip harder.
Yeah.
That means that you have to have higher regeneration temperatures, or you have to lower your regenerator pressure. So both will have some negative impact. So, for example, if you have higher regeneration temperatures, you will have more thermal degradation. Or if you lower your regeneration pressure to compensate for higher temperatures, you will have to have higher compression power needed. So this is one question: did you investigate this impact yet? And second, you mentioned the increase in energy consumption for achieving deeper CO2 removal. What about CAPEX impact? I would expect that you need more packing in your absorber to accomplish the mass transfer.
So starting with your second question, so in the end, this will be exactly the outcome of the economic analysis for sure. But this is also linked with your first question. For sure, you need a lean solvent that is as lean as possible, especially if you go above 99.9% capture rates. But you can also from the beginning increase the height of your absorber, spending more structured packing. So this will also help. And so it's not just one answer. We tested in the end different absorber heights. I think also the model tells you what could be possible, but it depends also what is your target. Do you want to achieve 100 ppm? Yeah, then with our setup, we would have also to increase the desorber pressure, which might have then the consequence of higher degradation rate. But if perhaps less than 1000 ppm is sufficient, then you can do it also with just 3 beds at our pilot plants. So the question is, what is in the end? I mentioned already during my presentation, what is the need of the society? Because to be honest, we have more trade-off. There is always at the moment the discussion how flexible should be a plant be. So when we talk about a waste to energy plant, this is different from a natural gas-fired unit. We have the topic lowest emissions, highest energy efficiency, highest capture rates, and lowest cost. And to be honest, you can dream that you have the optimal parameters for all these individual targets, but you will not achieve this. And my recommendation, I must say it, is also, hey, perhaps we should start with plants, also just to start to install more capture plants, which perhaps cannot achieve then less than 100 ppm, but doing something and not discussing and over-regulate in the end the implementation of the technology. Defining more and more targets which are hard to achieve, and then in the end the consequence would be that nobody will install anything, and that's also I have to add, in the end you can spend more equipment or more capex with structured packing, heat exchanger sizes, and so on. This will help you vacuum or reducing the pressure. We have not tested, and we will also not test in our pilot plan. Increasing the temperature, helps to make it leaner. We tested it, but it is not a one-fits-all answer. It depends, especially for your use case. And this must be step-by-step analyzed. What's available at your site? Does it make sense? And in the end, also what are the requirements from the regulator?
Yeah, thanks, Peter. We're a little bit over time, so I think we should stop. But Said and Andre, we didn't forget your questions, so Diego and Katarina will come back to it after the webinar. So I would like to thank everybody for attending this webinar. Of course, the people who listened in and asked the interesting questions. Thank you very much. Also would like all the presenters for their presentations and answering the questions, and also IED as the organizers of the webinar to make this all possible. So keep an eye on our website, keep an eye on our newsletter, and there will be more of these webinars ahead during the remaining time of the project. So thank you very much, and have a great rest of your day.
Bye.
Bye-bye.
Thank you. Bye.